video, you'll be able to understand how we are generating a sinusoidal waveform in any generating power plant, and also some of the important characteristics of generation. So let's see here the working principle of AC generator, main parts, and why are these parts required for. It works on the basic principle of electromagnetic induction. So electromagnetic induction, that is change of flux linking a conductor will have induced EMF as told by Faraday's first law, and as stated by Faraday's second law, the direction of the magnitude of induced EMF is directly proportional to rate of change. So as faster the flux changes, when it's linking the coil, we'll have more magnitude of induced EMF. If the rate of change of flux linkage is less, we'll have less induced EMF. So when there's a relative motion between a coil and a magnet, when we have relative motion between coil and magnet, any one should be in motion or change, and thus we have induced EMF. If the change is faster, we'll have more induced EMF. If the change is less, it will have lesser magnitude of induced EMF. What are the main parts? So the main parts are armature, which is nothing but a rotor. We'll have shaft, where we collect the mechanical energy, and then we'll have field winding, which is nothing but your stator windings. We'll have slip rings, from where we collect the currents. Then we have carbon brushes to accommodate the conductors. Now, why are these main parts required for? So can you just think, as we just discussed above, what are the main parts? So why is the shaft or armature required? Field. The field windings are required. They're required because for smaller applications we can have permanent magnet, but for larger applications we need electromagnets. So they provide the required magnetic field. Slip rings, as told, they're connected to the conductors to collect the current that is being produced. Carbon brushes, through which we can connect the conductor as well as the loads. Now, slip rings are connected to dash, and thus they rotate within it. Slip rings are actually connected to armature. Carbon brushes are connected between dash and dash. So carbon brushes are connected between slip ring and load. Now, as we have already discussed, the direction of induced EMF is given by dash hand rule. It's given by Fleming right hand rule. Okay. Now we'll discuss some more. What is Fleming's right hand rule? What are the three fingers shortly? But however, one should know that when do we get maximum induced EMF and when do we get a zero induced EMF induced in the conductor when you have change of flux and it's linking the coil. So I'm taking two cases. We'll see what are these two cases. Case 1, the conductor is moving parallel to the flux. Case 2, if the conductor is moving perpendicular to the flux. So let's analyze. These are direction of motion. This is my coil, and these are the flux lines. Now case 1, as you can see, it is moving along the flux. There is no change of flux at all. You can see at any instant in that motion it is not changing. So if I say, for example, here these are the flux lines and these many flux are linking. There is 1, 2, 3, 4, 5. So I have 5 flux or 5 above which are linking. At any instant you can see I have 5 only. So there is no change of flux linkage here. Thus I can say that when the force, how is the force acting? The force is acting downwards. So when the force is being parallel to the flux, we get zero induced EMF. So let's see the second case now. So now you can see that it's a conductor. I repeat, the conductor is moving perpendicular to the flux. Or I can say that the applied force is actually perpendicular to the flux. Here it makes 90 degrees. Thus we get maximum induced EMF in this case. So you should know that case 1 and case 2, when we are moving parallel we get 0, and when the flux is cutting perpendicular we get maximum. So let's analyze here with Fleming right hand rule to find the direction of induced EMF, and if the circuit is closed, the direction of induced current also. So right now we'll just find the direction of voltage. Now, as we know that Fleming right hand rule is given as thumb indicates the direction of force, that we apply. So here direction of force, as you can see is visually, that this coil side is 1 and this coil side is 2. We have one coil which has two sides, coil number 1 and 2, coil side 1 and 2. So coil 1 is going upward and coil 2 is going in downwards direction. So we'll find what is the direction of current or what is the direction of induced voltage here. And the the index finger indicates the direction of magnetic field, and then the middle finger, this part, indicates the direction of induced voltage and induced current only when the circuit is closed. So analyzing this with respect to north pole, so the force, as told, it's going in upward direction. This is the direction of force, and then this is the direction of magnetic field, and then if you use your right hand rule, and then the direction of current would be actually away from your plane. So this is the direction of magnetic field, and the current would flow in this direction and then come out here if the circuit is closed. And if we have a load connected here, in this way, if we have a load, so current enters to point N and then it would leave point N. So in that way we could assume for positive half this is positive and this is negative. Okay, so let us analyze with coil 2 also. So for coil 2, the direction of force applied is downwards, as you can see, and then if you use a Fleming left hand rule, the direction of magnetic field is towards right. The current or the direction of induced EMF is actually coming towards the plane. So that means this is the direction of induced EMF, direction of induced current, and here this is the direction of induced current or EMF. So let's use Fleming right hand rule now. So now, as it is evident that thumb indicates the direction of force, middle index finger indicates the direction of magnetic field, and then the middle finger indicates, this is your middle finger, it indicates the direction of induced EMF or current. Now similarly, if we use, so thumb indicates the direction of force, this is the direction of force, this is the direction of induced EMF or current, this was the magnetic field. So this is a magnetic field, and you can see this is your middle finger, which indicates that the current is coming towards the plane of the flowing through coil side 2. Look here. So if the directions are given, how can we find the rotation force? So let's analyze in that way. So this is the magnetic field, that is north to south, and then this is they are saying that this is the direction of current. Fleming right hand rule, can one pause the video and analyze what direction is your coil AB, CD rotating? So coil side AB, how is it moving, and coil side CD, how would it move? So direction of field is north to south. This is the direction of induced EMF. So then what is the direction of your rotation of the coil? So please pause the video, analyze, and then you can check. Yes, if your answer is that AB is moving in this direction and CD would be going in downwards direction, then your answer is correct. In the sense, the coil is being rotated in anti-clockwise direction. So let's analyze at this point. So this is the magnetic field. The current is going in this direction, or your induced EMF is going in this direction, that is towards the plane. And if you open up all the three fingers, you will have force going in downwards direction. Okay, so then the current enters point M and it would leave point N. So I will mark here as positive and negative for positive half cycle. So figure A, current flows from conductor AB through brush point 2 to 1, and then it flows through point M to N through conductor DC. So consider this as positive half cycle. That means, so we have this waveform generated. So after 180 degrees, the circuit is as shown below. That is, AB coil, which was under north pole influence, will be under south pole influence after 180 degree. C and D, which was under the influence of south pole, after 180 would be under influence of north pole. So if you open your three fingers to analyze the direction of induced EMF, these would be correct. And now this current hits your carbon brush 1 and it enters north pole. So I will be marking here positive and here negative. So if you see, after 180 degrees, this was positive here and negative here. After 180, it has been changed. That means it's been alternating. Thus we have alternating sine wave which has been generated. So current flows from C to D, brush point 1 to 2, and then through conductor B to A. Thank you for watching the video. To understand how do we, the working principle of generation of a sinusoidal waveform, please subscribe the channel to enhance your knowledge further.